All right, these are the last topics in Chapter 5 that we're going to go over. Oxidation reduction, which is also called redox, reaction rates, energy and chemical reactions, and equilibrium. Oxidation reduction reactions are very, very common. Some people get confused which is one, which is the other, but there are easy ways to remember it. So oxidation means the loss of electrons. It used to mean reacting with oxygen, and it still does, but when you say loss of electrons, you mean that other things besides oxygen can be oxidized. So you notice the line up here in the upper right-hand corner. One way to remember which is that we have a little mnemonic here. Leo the lion says GER, loss of electrons oxidation, gain of electrons reduction. You can't have something losing electrons unless something is also gaining them. And normally we will see something like metals losing electrons to nonmetals. Well, also, as you saw in the lab, you can have metals losing electrons to metal ions. So something has to gain the electrons and something has to lose it. Let's take a look at this example here. I have a sodium atom. Over here, 11 protons, 11 electrons, so that's a neutral sodium atom. And I have a neutral chlorine atom, 17 protons and 17 electrons. And what's going to happen is that the sodium atom is going to lose an electron to the chlorine. And that's what it's saying right here. We follow the arrow, and we wind up making two ions. We make a sodium ion and a chloride ion. And if you recall back when we did bonding, we could explain this in that the sodium ion and the chloride ion now have the electron arrangement as a noble gas, and so they're more stable. So this is a favored reaction. All you have to do is heat the sodium a bit to get this going, and then it will go on its own. Now, one thing about oxidation reactions is they all release energy. And so we use those in this world to get energy, either to heat our homes, to move our cars, or even for us to move ourselves. So the sodium atom, because it lost an electron, is said to be oxidized. The chlorine atom, and whoops, let me go back to that. There's a little equation down here at the bottom that shows the sodium atom losing an electron and becoming a sodium ion. Now, that's one way to recognize that something is being oxidized, because you'll see minus an electron. Sometimes you might see plus an electron on the right-hand side, so that kind of means the same thing. And then we have the chlorine atom gaining the electron, so the chlorine is said to be reduced, and we could write that down here with a little equation as well. So here's the chlorine atom gaining an electron. Now I'm putting in zeros for the atoms in the beginning because they're neutral. You might not see that written in the book, so you just want to be aware of that. Here's another famous reaction. This is called the thermite reaction, and it releases an awful lot of heat. And if we were to do this in the lab, we'd have to be pretty careful of it. You notice they have like a clay flower pot here. What you don't see is below this would be a bucket, either containing water or sand to catch this stuff. You wind up making molten iron, so the temperature is over 1,000 degrees easily. And this is enough to melt metals. Now the reaction itself looks like this. We have actually not a solid aluminum like a piece of aluminum foil or a bar of aluminum, but it's aluminum powder. And the aluminum powder is reacting with some iron ions. Now you can't just have iron ions by themselves, so this would be a form of iron in a compound. And if you look and see what happens, now the aluminum has a charge, now the iron is neutral. And if we take a closer look at them, we can see that the aluminum is losing 3 electrons when it goes from being neutral to positive 3. So the aluminum is said to be oxidized. And the iron 3 ion is gaining those electrons and is said to be reduced. Again, very, very exothermic. And here's another common example. And so anytime we burn materials, that's an example of an oxidation reaction. Now here we're actually combining carbon with oxygen. And you see how we're starting off with carbon and hydrogen atoms, and let's say that they have oxidation numbers of this. These are their charges within the compound. And what happens? They're becoming CO2 and water. Now, if we look at the CO2, we'll see that the carbon has gone from being -4 to +4. And the oxygen has gone from being 0 to -2. Now the hydrogen, which was +1 here, is still the same over here. So the oxidation part is really involving the carbon losing electrons and the oxygen gaining them. And as I went over in class, This is where we derive our energy from. So we burn sugars. In a sense, we take electrons out of carbon atoms and give them to oxygen atoms. So our reaction would look like this. And can you recognize this as oxidation? Now, it's oxidation because we're losing electrons. You notice that the charge goes up. That's another way to indicate oxidation. And then the opposite is happening. The oxygen atoms are gaining electrons as they become oxide ions. Now, just as in any chemical equation, everything must be balanced. And I should have put a 2 right in there. Let me pop that 2 in. And so I'll put black this time. And so I should have a 2 here as well to balance off the equation. Okay. So, and that would be reduction. So here's one for you to try. And this would be similar that you might see on the exam. Identify the following processes as either oxidation or reduction. So why don't you pause the video for a sec and give that a try. I want to go up and get rid of my pen. And get rid of that. Here we go. And so here are the answers. Okay, the first one is oxidation because you notice the electrons are produced as a product. Now we also could have written that, just to show you, probably should have kept my pen. We also could have written it like this, Sn minus 4 electrons becoming Sn plus 4. Because that would be the same as this one. So whether you show electrons as a product or losing electrons on the reactant side, it means the same thing. And then we can see here, reduction, because it's gaining electrons, it's also reduction here as well. You notice I didn't put the 0 in, but this is really neutral. As we go, the charge goes down in reduction, you notice? Charge is going down. Okay, another way to identify it. Okay. Now here's another example for you. You notice they're talking about light-sensitive sunglasses. And there are some sunglasses in regular glasses that get darker as they're exposed to sunlight. I wonder, how does that happen? Because the reaction is reversible. It goes back and forth. So in this case, ultraviolet light can initiate the reaction. And so the glasses would contain silver ions and chloride ions. And so what happens is the silver ions are becoming silver atoms. That would be neutral, right? And the chloride ions are becoming Cl2, chlorine atoms, again neutral. So which reactant is oxidized, which reactant is reduced? So we weren't talking about the silver ions and the chloride ions. So why don't you pause the video for a second and take a shot at it. All right, and here are the answers. So the reaction that's oxidized is the chlorine ions, the chloride ions. You notice that they are going from -1 to 0, so they're losing electrons. Whereas the one that's being reduced, the silver ion, it's gaining electrons. Now once you recognize one is oxidation, the other one has to be reduction. So that's another way to do that. Okay, I'm going to get rid of my pen again. All right. Now next topic we're going to look at is going to be answering these questions. Why are some reactions fast and others slow? Why do some reactions release heat while others absorb heat or get cold? So the first topic is called kinetics, and that's the study of reaction rates. Why do things go faster or slower normally? And we control the speed of reactions many times at home. A stove is an example of an apparatus that speeds up chemical reactions, and a refrigerator is an example of let's say a machine that slows reactions down. So the factors that are involved in the speed of reactions are concentration. That can affect how fast a slow reaction goes. Temperature, is something hotter or something cold. Pressure, this involves gases. Is the pressure high or pressure low? And surface area. So this really affects solids. Do you have a chunky solid or do you have a powdered solid? And the last factor is catalyst. Now a catalyst is something that is not a member of the chemical reaction, but it can lower the energy requirement needed for the reaction to go. And in biology, many catalysts are called enzymes. In chemistry, we just call them catalysts. And we're going to take a look at the collision theory, which will explain why reactions happen anyway and what are some of the factors involved there. And we'll also check out some potential energy diagrams. So these factors, they usually, if you increase any of these things, that will usually speed up a chemical reaction. And so higher temperature, heating things helps to make reactions go faster. Increasing the pressure is like adding more stuff. Grinding up, a sugar cube will make the sugar dissolve faster than leaving the sugar cube by itself. You're increasing the surface area. Okay. So these are the conditions necessary for a reaction to happen. You must have a collision. So the reactants have to collide. They have to be oriented correctly when they do collide, because sometimes nothing will happen. And when they are oriented correctly and they collide correctly, then they might be able to break the bonds that they contain and then start to form new bonds. Now, one thing about that collision, the collision must be violent enough so that there's enough energy involved in it so that you can start breaking those bonds. And the energy needed to start the reaction is called the activation energy, or they're calling it energy of activation. Now, reactions that have a high activation energy will be hard to get going because it's just hard to put in the energy needed to start the reaction. Those with low activation energies may be dangerous because they might be able to react at room temperature. So here's the diagram that we're going to see on the collision theory. So let's take a look at this. I got this out of a book years ago. So for A, we have 3 molecules. Looks like they're on a collision. They're going to crash into each other. They bang into each other, and you notice they form something in here that doesn't last very long, and we wind up getting 2 products. So the products don't look anything like the reactants. And then down in B, we have the same particles on a collision course. They smack into each other, but notice what they form doesn't look like this thing. It looks like they formed something else. And then they break away, and they look exactly like they did when they started. So if the colliding particles have enough kinetic energy and collide at the right orientation, they can react to form a new product. So which one of these is that happening to? That would be in A. Here we have an effective collision. They're going fast enough, and that's supposed to be indicated by the length of these little dashes here. You notice it's shorter down here. So here the molecules are moving fast enough, and they collide just the right way. So we have an effective collision, and we wind up with our products formed. And then down in B, the collision is ineffective. It might be due to the particles moving a little bit too slowly, so that when they bang into each other, they form something where the bond energy isn't enough to break the bonds within the reactant molecules. Or maybe they're hitting at the wrong angle, because this kind of thing looks different than that. So this will give us an activator complex that looks different than the one we need. So you have to have both of these conditions, enough kinetic energy and collide at the right orientation for a reaction to happen. Now here's an example of somebody who took a little wood splint and they lit the splint on fire, and then they blew out the flame, but you notice it's still glowing a bit. And then they have a bottle of oxygen gas, and they put that glowing splint into the bottle, and it burst into flames. So, in air, a lighted splint glows and then goes out. Place some pure oxygen, the splint bursts back into flames. Can you account for the difference in reactivity? What do you think? Well, the answer would be in letter B, we have a greater concentration of oxygen. You need oxygen for the splint to burn. So because there's a greater concentration, not just that there's more, but a greater concentration of oxygen within the bottle, that you're going to have a greater chemical reaction, and thus it bursts right back into flames. Now here's an example. These kind of explosions happen all the time. You notice this happened back in February of 2008 down south, Savannah, Georgia, where these sugar refineries, they can just blow up, it seems, on their own. And to explain what's going on here, you notice this is right out of the newspaper. They suspected it was sugar dust. Well, sugar contains carbon atoms which can be oxidized, and that means that you can burn sugar, chemically burn it or burn it with a match. So what happens in the refinery is that you have sugar dust mixing with air. So sugar dust is almost like a gas, and because you can mix it so well with air or oxygen, all you need is a spark to get this going, and you have an explosion. So by having dust like that, we have almost an infinite surface area. So increase in the surface area speeds up the chemical reaction. So that could have been just a spark from, anything starting this off. You get a spark produced when you turn on a light switch at home. You might not notice that spark unless it's a dark room, but there's a little bit of a spark produced. And that can be enough sometimes to start a reaction. All right, let's take a look at the two different types of reactions based on whether they absorb or release energy. The first type is called an exothermic reaction. In an exothermic reaction, energy is released. The energy of the products is less than that of the reactants. We're going to take a look at this diagram in a sec. And heat is looked at as a product. And here's an example here. We were writing, notice our kilocalories, that represents the heat, as a product. So if you see a chemical reaction written where they have plus a certain amount of energy on the product side, that's going to tell you it's exothermic. Now this is called the potential energy diagram. And if we start right here, notice there's no numbers on here because it doesn't have to be numbers for us to understand it. It's the shape of the curve that you want to, whoops, let me go back on that. It's the shape of the curve that we want to notice. So let's say we're starting here with our reactants and they're on their collision course. And so when they smack into each other, there must be enough energy for them to collide and start the reaction going. And so this distance here represents what we call the activation energy. And then if they have enough activation energy and they collide with the right orientation, they may start to form the products. Now in this case, we go down the curve even further, and here are our products down here. Now if you notice over here on the left it says energy. So our products have less energy than our reactants do. And the difference between the energy of the reactants and the energy of the products is what's released to the environment. So an exothermic reaction releases more energy than it takes for the reaction to go. So you got to kind of think of this as a hill to climb. It's not very hard to climb in this direction. Pretty hard to go in this direction though. Now an endothermic reaction, if you look at this curve up here, is just the opposite. Endothermic reaction, heat is absorbed overall. The energy of the reactants is greater than the products. So you could say the energy of the products is, the energy of the reactants is less than that of the products. While the energy of the products is greater than that of the reactants. And so here what we have is, I arrow back again, here we have a very high activation energy. A lot of energy has to be involved in the collision. And then we make our products, the products are up here. So the difference that we get is the energy that's absorbed from the surroundings. So if you were to do an endothermic reaction in a test tube and you had the test tube in your hand, it would feel cold. It would absorb heat from the test tube and thus from your hand. So endothermic reactions feel cold to us. Now, if I asked you which one is favored, would the reverse reaction or the forward reaction be favored? Well, you'd say, well, I think the reverse one because there's a shorter hill to climb and go back this way rather than go in that direction. And if you take a look down here at our equation, you can recognize an endothermic reaction looking at a chemical equation because they'll write the energy, the heat, on the left side as if it was a reactant. So this really says in order to get these two gases to combine together to form NO, you have to add this much heat for every mole of these things. Now we know the catalysts speed up a chemical reaction, so let's see how it might do that. So a catalyst makes a chemical reaction go faster because it lowers the activation energy. Now if we take a look at our graph, we can see that. Here's my arrow again. So the one in blue represents the activation energy, this distance here, of the uncatalyzed reaction. See how high that is. But when we add the catalyst, it lowers the activation energy. We wind up making the same products. It's just that we make them a lot faster because it takes a lot less energy for that to happen. So all the chemical reactions that happen within us use catalysts or enzymes, and that's because they all happen at the same temperature. And that catalyst then would be released at the end to be able to be used by other reactants. So you don't need much of a catalyst. Now for us also, vitamins are catalysts. They're what they're called coenzymes. So they help an enzyme react. So you need a very little amount of a vitamin, but you do need vitamins. We can make some on our own, but most of them we have to get from eating different fruits and vegetables. All right, so let's see how much you picked up. So can you identify these reactions as exo or endothermic? So why don't you pause the show for a second and take a shot at it. All right, here are the answers. Now the first one is exothermic, and that's because the energy is written on the product side. The second one is endothermic because the energy is written on the reactant side. And the third one is exothermic. It's just the word heat is enough to tell us if it's on the product side that energy is released. Okay. Now, this is a few questions on kinetics. What do you think the effect of each of these on the rate of the reaction would be? Will it increase, decrease, or not affect the reaction at all? So again, pause the slideshow and answer these questions, and then come back and check your answers. Okay, and here we go. So increasing the temperature usually increases the rate of the reaction because you provide molecules with the activation energy they need to start the reaction. Now, removing some of the reactants will slow the reaction down because they're not going to have enough collisions if you have fewer reactants present. Adding a catalyst usually increases the speed of a reaction because you lower the energy requirement or the activation energy. Placing a reaction flask in ice would slow a reaction down because, again, you are robbing the reactants of the activation energy they need to react. Increasing the concentration of only one of the reactants would also increase the speed. So you don't have to increase the speed by increasing the concentration of both reactants. Just one would be enough. So what about this now? Here we have a chemical reaction. Can you indicate the effect of each factor listed on the rate of the following reaction as increase, decrease, or no change? So, if I raise the temperature, will I increase the rate of the reaction? If I add oxygen, will I increase the rate or decrease it? Adding a catalyst, I'll lower the temperature. Notice A and D are opposites. So you might say, well, I don't know about the temperature because I don't see a heat effect in here. And so what if I were to write the word heat in to make it a little bit easier for you? So I'm going to do that. So I would put the word heat over here. So I'd say heat plus 2CO and O2 gas will give me CO2 gas. So this would make it easier to answer the question about the temperature one. All right, so let's see what we get for an answer. Okay, yeah, increasing the temperature would increase the rate of the reaction. Here, because you see, heating it causes the reaction to go in this direction like that. So raising the temperature should increase the temperature. It should increase the reaction rate. Now you might think, I thought that was true for all reactions. Technically, it isn't. Some reactions actually go better at lower temperatures. So we should really have the word heat in here. Adding an oxygen would increase the rate. In fact, adding either one of these two would make the reaction go faster. And lowering the temperature would slow the reaction down, as we went over. Okay. Now, one thing that we did an experiment on, and I'm not going to go into it very deeply though, is equilibrium. And so I have, and we talked about gases, so this is a good slide to look at. So equilibrium means you have two reactions going in at the same speed in opposite directions. So I know we talked about gases the other day. I talked about people having problems breathing when they're mountain climbing at high elevations like Mount Everest. And we can take a look at it in terms of a chemical reaction. So Hb represents hemoglobin. So we have hemoglobin in the bloodstream, and hemoglobin has to combine with oxygen to form what they call oxyhemoglobin, and this is what goes to the cells, and that oxygen is released to the cells so they can burn the food and make energy. So at equilibrium, the rate of formation of oxyhemoglobin is equal to the rate that it's being released. So what happens when you go up on a mountaintop? Well, there's less oxygen present. You know, there's the forward and the reverse. Forward is always when it goes to the right. So at high elevations, the forward reaction is slow because there's less oxygen available. That means you don't make as much oxyhemoglobin. But the blood that's being carried to the cells keeps on releasing the oxygen it has. And so you wind up having a difficult time because you don't make much of this, and what you do make just releases the oxygen it has anyway. And so you really have the reverse reaction going faster than the forward when you're high on high elevations. And question, how can you capture more of the oxygen that is available? Well, maybe adding more hemoglobin. But how can you add hemoglobin? That might mean adding more of your own blood cells. So maybe what people can do is either stay at these high elevations and live there for a while, so their bodies will try to acclimate themselves by making more red blood cells. Or they could even have a transfusion of their own blood before they go before they go mountain climbing. That kind of thing could happen. Okay, and that's going to be the end of the slideshow.